Did you know our solar system is trapped inside a giant, magnetic tube, stretching hundreds of light-years across the galaxy? This isn't a theory from a science fiction novel. It's a real structure, mapped in astonishing detail using data from the Gaia Space Telescope, and a German-Russian X-ray observatory called eROSITA. Scientists call it the Local Interstellar Chimney, and it appears to funnel hot, ionized plasma in a direction that points almost exactly toward the constellation Centaurus, home of Alpha Centauri, our nearest stellar neighbor. So what exactly are we living inside? And why does it seem to be pointing, of all places, toward the next star system over? Let's start with where we actually are. Our Sun, along with thousands of nearby stars, sits inside something astronomers call the local bubble. It's not a metaphor, it's a physical cavity, roughly 1,000 light-years wide, filled with gas so thin and so hot that it barely resembles the interstellar medium found elsewhere in the galaxy. For decades, researchers suspected something like this existed, because when they looked in almost every direction from Earth, they found strangely little cold, dense gas nearby. It was as if we were sitting inside a pocket of near emptiness. Early X-ray missions picked up faint traces of hot, diffuse plasma glowing all around us, and that glow became one of the first real clues that the Sun wasn't just floating in ordinary interstellar space. The breakthrough came when researchers combined precise 3D maps of interstellar dust with Gaia's extraordinarily accurate measurements of stellar positions and motions. In a landmark 2022 study published in Nature, a team led by astronomer Catherine Zucker at the Center for Astrophysics traced the movement of young stars and star-forming regions back through time, and reconstructed how the local bubble grew. What they found reshaped how we think about our cosmic neighborhood. Every single young star and star-forming region within about 500 light-years of Earth sits directly on the surface of this bubble. Not scattered randomly through space, but arranged, almost like frost on the inside of a balloon, along the edge of an expanding shell. Then, in 2024, a follow-up study led by researcher Theo O'Neill, using an even higher resolution 3D dust map, found something the original model hadn't fully captured. The local bubble isn't a clean, symmetrical sphere. Its surface is wildly irregular, and it stretches outward in one direction far more than in others, forming an elongated extension toward the northern galactic sky. The researchers gave this feature a name that stuck: the local chimney. Picture the local bubble not as a balloon, but as a lopsided cavity with a long neck reaching up and out of the galactic plane, like smoke rising from a chimney into open sky. And we are living, right now, somewhere inside that structure. So how did something this vast come to exist in the first place? The answer is violent, and it happened closer to home than you might expect. Roughly 14 million years ago, give or take, a cluster of massive stars in a nearby stellar association began dying in a rapid sequence of supernova explosions. These stars belong to groups astronomers call the Scorpio-Centaurus Association, specifically regions known as Upper Centaurus Lupus and Lower Centaurus Crux. One by one, over a span of several million years, somewhere between 14 and 30 of these massive stars detonated, each blast slamming into the surrounding interstellar gas and pushing it outward like ripples from repeated explosions in water. Layer by layer, explosion by explosion, those shockwaves swept up the surrounding material and carved out the low-density cavity we now call home. This isn't speculation dressed up as fact, either. Scientists have found physical evidence of these ancient blasts buried in the geological record right here on Earth. Deep-sea sediments and even samples from the Moon contain traces of an isotope called iron-60, a radioactive form of iron that is essentially never produced naturally on Earth, but is produced abundantly in supernova explosions. The presence of iron-60 in ocean crust, deposited within the last few million years, lines up remarkably well with the timeline of the supernovae that built the local bubble. In other words, we can hold, quite literally, physical debris from the explosions that shaped the neighborhood we live in today. And here's the detail that makes this story personal. When those supernovae first went off, our Sun wasn't even inside the bubble yet. It was orbiting the galactic center on its own path, roughly 5 million years away from arriving at this particular patch of space. Only in the last 5 million years or so did the Sun's orbit carry it directly into the expanding cavity that earlier generations of dying stars had already carved out. Today, almost by coincidence, the Sun sits very close to the center of that bubble. We didn't create this structure. We simply drifted into it, and ended up parked, almost perfectly, in the middle of someone else's cosmic wreckage. Now here's where the story gets even stranger, and connects directly to our nearest neighboring star system. Using the eROSITA X-ray telescope, positioned far from Earth's magnetic interference at the second Lagrange point, researchers built the most detailed three-dimensional map yet of the hot plasma filling the local bubble. And within that map, they found something unexpected: elongated tunnels of even hotter, even lower density plasma extending outward from the bubble's main body, like corridors branching off from a central chamber. The most striking of these tunnels points in a very specific direction, toward the constellation Centaurus, the same patch of sky that contains Alpha Centauri, the closest star system to our own, just over 4 light-years away. It's important to be precise about what this means, because the real science here is already remarkable enough without exaggeration. This tunnel isn't a solid pipe, and it isn't proof of a direct physical corridor built specifically to Alpha Centauri. What researchers have found is a region of exceptionally hot, extremely thin plasma extending in that general direction, carved by the same kind of shockwaves and stellar winds that shaped the rest of the local bubble. But the alignment is striking enough that multiple independent studies, using different telescopes and different mapping techniques, have identified structures pointing towards Centaurus specifically. Some researchers suspect these tunnels form where nearby superbubbles collide or overlap, essentially venting hot gas along the path of least resistance, and that path just happens to run toward our closest stellar neighbors. Think about what that actually means for a moment. If future spacecraft ever attempt the long, difficult journey toward Alpha Centauri, they may not be pushing through the same dense, resistant interstellar medium that fills most of the galaxy. They could be traveling through a corridor of unusually hot, unusually sparse plasma, shaped over millions of years by ancient stellar explosions. It's not a highway in the way we'd normally imagine one. There's no pavement, no direction signs, nothing solid at all. But in terms of gas density and resistance, it may genuinely represent a path of comparatively lower friction between two star systems. So what would it actually be like to move through this environment? Inside the local bubble, gas density drops to levels far below what's typical elsewhere in the galaxy, sometimes to less than a tenth of the average interstellar density. Temperatures inside the bubble, meanwhile, can reach hundreds of thousands, even into the low millions of degrees, because the gas has been shock-heated by repeated supernova blasts. That combination, searing hot, but almost impossibly thin, is exactly what allows this plasma to glow faintly in X-rays, which is how eROSITA and earlier missions were able to detect it at all. For any future interstellar probe, this low-density environment could matter enormously. Spacecraft traveling at even a modest fraction of the speed of light face a serious hazard from collisions with interstellar dust and gas, because at extreme velocities even a single dust grain can deliver a devastating amount of energy on impact. A region with fewer particles per cubic centimeter means fewer of those high-speed collisions, which could translate into less erosion, less shielding required, and potentially a safer, faster route for any spacecraft daring enough to attempt the crossing. Some researchers studying interstellar travel concepts have already pointed out that mapping the density structure of the local interstellar medium, tunnels included, will be essential groundwork for planning any realistic mission toward Alpha Centauri. There's also the question of protection. Our solar system sits inside a bubble carved by supernovae, and that bubble interacts constantly with the solar wind, the constant stream of charged particles flowing outward from the sun. The heliosphere, the vast magnetic bubble generated by our sun's own wind, pushes back against the surrounding interstellar plasma, carving out its own smaller cavity within the larger local bubble. Some researchers have proposed that the relatively gentle, low-density conditions inside the local bubble may have historically helped shield the solar system from more extreme cosmic ray bombardment than we'd otherwise experience if we were sitting in a denser part of the galaxy. It's a reminder that the structures around us aren't just passive scenery, they actively shape the radiation environment every planet in this system experiences. There's another piece of this puzzle worth pausing on: the shape of the local chimney itself. According to the 2024 dust mapping study, the surface of the local bubble sits at an average distance of about 550 light-years from the Sun, though it varies enormously, from as close as roughly 200 light-years in some directions, to well over 2,000 light-years in others. That's not a neat, tidy sphere, it's a lumpy, asymmetric cavity, thickened in places, paper-thin in others, and stretched dramatically along the axis that forms the chimney. The total mass of dust traced along this surface adds up to roughly 600,000 times the mass of our Sun, swept up and compressed into a shell by millions of years of relentless shock waves. When you picture the local bubble now, don't picture a smooth balloon. Picture something closer to a torn, uneven pocket, with one long, narrow neck venting material up and out of the crowded galactic disk into the emptier space above and below it. That venting process matters, because it connects directly back to the tunnel pointing toward Centaurus. Researchers studying these structures believe that when a bubble like ours eventually breaks through the surrounding layer of denser gas, hot interior plasma can escape along the path of least resistance, essentially blasting a channel outward the way steam escapes through a crack in a kettle. Some of that escaping material appears to vent vertically, out of the galactic plane entirely, forming the chimney. But other channels seem to escape sideways, along the plane itself, toward neighboring cavities and star systems, and the Centaurus-facing tunnel may be exactly this kind of lateral vent. It's the same physical process, just pointed in a different direction, and it happens to be aimed at the star system we're most likely to visit first. None of this is settled science with every detail locked in. Researchers are still debating the precise age of the local bubble, with the original 2022 study estimating around 14 million years, while more recent modeling published in 2025 suggests the bubble may actually be much younger, somewhere between 3 and 6 million years old, and powered by an even larger number of supernovae than first thought, possibly 19 to 30 explosions rather than 14 or 15. Scientists are also still mapping exactly how many of these tunnels exist, where they lead, and whether the one pointing towards Centaurus is unique, or simply the clearest example of a much more common feature threading through the galaxy's spiral arms. That uncertainty isn't a weakness in the science, it's exactly how good science works. Models get refined as better data arrives, and every refinement gets us closer to an accurate picture of the space around us. What this discovery really represents is a fundamental shift in how we think about our place in the galaxy. For most of human history, we imagine space as essentially uniform, stars scattered through a roughly even distribution of gas and dust, with our solar system just one unremarkable point among billions. What the local bubble and its chimney reveal is something far more specific and far more dramatic. We live inside the aftermath of a chain of ancient explosions, in a cavity actively shaped by the deaths of massive stars that lived and died long before humans existed. And quite possibly, extending from that cavity, there's a channel of thinner, hotter plasma reaching out in the exact direction of the nearest star system beyond our own. Future missions, whether they involve laser-propelled sail concepts like those explored by Breakthrough Starshot, or more conventional long-duration probes, will need exactly this kind of density mapping to plan a realistic route. Knowing where the interstellar medium is thick and where it thins out could be the difference between a mission that survives the journey and one that doesn't. And as more data comes in, from Gaia's ongoing surveys, from eROSITA's expanding X-ray catalog, and from future missions specifically designed to study the boundary of our heliosphere, this picture will only get sharper. So the next time you look up at the night sky, toward the general direction of Centaurus, consider this. Between us and that faint point of light lies more than just empty distance. It lies through the wreckage of ancient supernovae, through a bubble carved by stars that exploded millions of years before the first humans walked the Earth, and possibly, through a strange, thin corridor of scorching plasma leading almost directly toward our closest neighbors among the stars. We didn't build this path. We just happened to be born inside it.